Today we're going to learn how to use trigonometric identities to find values or simplify expressions. Given that sine of theta equals 4 over 5 and theta is between pi halves and pi, find the values of the other 5 trig functions of theta. Now we don't know what theta is, but we don't actually have to know, because we have a ratio and we have the location, which quadrant. So draw an angle that is in quadrant 2 and then draw your reference triangle. Sine of theta, which is equivalent to the reference triangle angle, is equal to y over r, opposite over hypotenuse. So if we've been given the ratio 4 over 5, then y equals 4 and r equals 5. Now all we need to do is use the Pythagorean theorem to solve for the other side of the right triangle. The square root of 9 is plus or minus 3, but because we're in quadrant 2 and the x's are negative in quadrant 2, our x is negative 3. And you may have already known that because 3, 4, 5 is a Pythagorean triple. So x is negative 3, y was 4, and r is 5. Cosecant of theta is the reciprocal of sine, so 5 over 4. Cosine of theta is negative 3 over 5. Secant would be that reciprocal, and tangent is y over x, so negative 4 over 3, making cotangent negative 3 over 4. We never even needed to know what theta was equal to in order to find the other 5 trigonometric ratios. For number 2, we're going to simplify using identities. Tangent of pi halves minus theta times sine of theta. Well, tangent of pi halves minus theta actually looks familiar to me. That is a cofunction identity, and that's equal to cotangent of theta. So I'm going to rewrite that as cotangent of theta times sine theta. This may seem pretty simplified, but I can actually rewrite cotangent in terms of sine and cosine and then either reduce or combine it with this sine theta. Cotangent of theta is cosine theta over sine theta. Sine theta over sine theta reduces to 1, so this original expression simplifies to be just cosine theta. For part B, I have one relationship that relates tangent squared theta to secant, and it's specifically the Pythagorean identity where tangent squared theta is equal to secant squared theta minus 1. So maybe if I substitute secant squared theta minus 1, I can get things in terms of secants and then simplify it from there. Distribute secant theta. Oh look, negative secant theta plus secant theta is 0. So this expression simplifies to be secant cubed theta. Remember, we put the exponent of 3 between the trig function and the argument of the trig function so that you don't think it's secant of theta being cubed, right? This is secant theta times secant theta times secant theta, not secant of theta times theta times theta. Verify a trigonometric identity. Ooh, look, this is verifying again. That means each step is part of your answer. Choose only one side to manipulate or simplify, usually the more, quote, complicated looking side. Do not rewrite the other side. So do not also algebraically manipulate or simplify the other side. So choose one side to work with. Use algebraic properties and trigonometric identities to manipulate the expression until it is identical to the other side. Often, rewriting expressions in terms of sine and cosine helps. But note, you cannot use inverse operations when verifying an identity. This is not an equation. You are not being asked to solve for theta. This is basically like a 2-column proof. The left side would be one column and the right side would be the other column, and we're working step by step to make one side identical to the other. Secant squared theta minus 1 over secant squared theta equals sine squared theta. So the more, quote, complicated looking side is definitely the left side. I want the left side to eventually be sine squared theta. The nice thing is we only have one term in our denominator. When you have a monomial in the denominator, you can just divide each term in the numerator by that denominator. So separately, this would be secant squared theta over secant squared theta minus 1 over secant squared theta is equal to sine squared theta. Secant squared theta divided by secant squared theta is 1. And 1 over secant squared theta, I can use a reciprocal identity. We know that 1 over secant theta is cosine theta. So 1 over secant squared theta would equal cosine squared theta. The left side is now 1 minus cosine squared theta. The right side is still sine squared theta. Write it each time. Oh my goodness, 1 minus cosine squared theta? That is sine squared theta. That's a Pythagorean identity. So our final step is sine squared theta equals sine squared theta. Every single step of your work is part of your answer. So make sure it's neat and make sure you write the left side and the right side in every step. For part B, secant x plus tan x equals cosine x over 1 minus sine x. To me, the right side looks slightly more, quote, complicated just because it's a fraction, but there doesn't seem like anything we can do with it, right? Because we have two terms in the denominator, so I can't do any dividing. But I love some Pythagorean identities. But Pythagorean identities require us to have a sine squared or a cosine squared when we do not have anything squared. So how can I turn this 1 minus sine x into 1 minus sine squared x? I can multiply it by its conjugate, and that will multiply to be difference of perfect squares. How did I come up with that idea? Because I've done a lot of these, and so I know a lot of weird tricks. Also, why do I want the denominator to be 1 minus sine squared x? Because I can turn that into cosine squared x. If this denominator is one term, then I can finally divide and maybe I won't have a fraction on the right side anymore. That's the tricky thing about trig identities. There are multiple ways you can do them, but it's not always clear. So sometimes you have to try multiple ways. So we multiply by 1 plus sine x. Of course, it's 1 plus sine x over 1 plus sine x because you can only multiply by a special form of the number 1 without changing something. Duh. In our denominator, we have 1 minus sine squared x. How do I know that? This is the difference of perfect squares. Now go ahead and distribute the cosine x into 1 plus sine x in the numerator. You could have also done that in this first step. Oh my goodness, now we have two terms divided by one term, so separated out cosine x over cosine squared x, cosine x times sine x over cosine squared x. Cosine x over cosine squared x is 1 over cosine x. Cosine x sine x over cosine squared x is sine x over cosine x. 1 over cosine x is the reciprocal identity for secant x, and sine x over cosine x is the quotient identity for tangent x. Oh my goodness, secant x plus tangent x equals secant x plus tangent x. Woo! If you box an identity, you box it in entirety. Find the exact value for the following. Sine of 15 degrees. What? That's not on the unit circle. Well, I do have these sum and difference formulas, so maybe I could use some angles that I know on the unit circle and then write 15 degrees as a sum or difference of those angles that I already know. So let's think of angles I know. In degrees, 30, 45, 60, 90, etc. Oh my goodness, I could rewrite 15 degrees as 45 degrees minus 30 degrees, or 60 degrees minus 45 degrees. So sine of 15 degrees is equal to sine of 45 degrees minus 30 degrees. Now I can use the sum or difference formula for sine of A minus B. That becomes sine of the first angle times cosine of the second, minus cosine of the first angle times sine of the second. Sine of 45 degrees is root 2 over 2, cosine of 30 is root 3 over 2, and sine of 30 is 1 over 2. Our answer is usually combined as one fraction, root 6 minus root 2 over 4. Tangent of 7 pi over 12. Again, not on the unit circle, but can I rewrite it as a sum or difference of angles that I do know that are on the unit circle? Well, in radians, angles that I know would be pi over 6, pi over 4, pi over 3, pi over 2, etc. In terms of 12, though, I'm going to rewrite pi over 6 as 2 pi over 12. And then pi over 4 would be 3 pi over 12. We'd have 4 pi over 12, 6 pi over 12. Those are the pi 12ths angles that I know. Oh, look, to get 7 pi over 12, I could add 3 pi over 12 and 4 pi over 12, which, as a reminder, is just adding pi fourths plus pi thirds. So tangent of 7 pi over 12 could be rewritten as tangent of the sum of pi fourths plus pi thirds. Using our sum formula for tangent, tangent of the first angle plus tangent of the second angle divided by 1 minus tangent of the first angle times tangent of the second angle. Tangent of pi fourths is 1. tangent of pi thirds is root 3. So we get 1 plus root 3 divided by 1 minus root 3. But you cannot have a root in the denominator, so we have to rationalize by multiplying by the conjugate. 1 plus root 3 over 1 plus root 3. Our numerator expands to be 1 plus root 3 plus root 3 plus 3 over difference of perfect squares, so square 1, that would be 1, minus root 3 squared, that'd be 3, which leaves you with 4 plus 2 root 3 over negative 2. Oh, look, we can divide each of the terms in the numerator by negative 2. So 4 divided by negative 2 is negative 2. 2 root 3 divided by negative 2 is negative root 3. Negative 2 minus root 3 is your answer. That is the exact value of tangent of 7 pi over 12. And you can always check that in a calculator. Type in negative 2 minus root 3, and then type in tangent of 7 pi over 12, and you'll get some crazy decimal, and if the decimals match, you did it correctly. For number 5, find cosine of a minus b, given that cosine of a is negative 4 over 5, and a is in the third quadrant between pi and 3 pi halves, and sine of b is 5 over 13, with b being in the first quadrant between 0 and pi halves. All right, so cosine of a minus b using our difference formula is cosine a times cosine b plus sine a times sine b. I don't know what a is and I don't know what b is, but I don't need those to find the other ratios. Let's create a reference triangle for angle A. Cosine A is negative 4 over 5. So x is negative 4 and r is 5. Hey, we can solve for the opposite side, or for y, by using the Pythagorean theorem. That's that same Pythagorean triple that we had before. So this side is 3, but since we're in quadrant 3 and the y's are negative here, y is negative 3. So cosine of A is negative 4 over 5, and sine of A would be negative 3 over 5, right? Y over r. Draw a reference triangle for angle B, which is in the first quadrant. Because you were given sine of B, you've been given y over r. So y is 5 and r is 13. Solve for x using the Pythagorean theorem, or you may remember this is also a Pythagorean triple, 5, 12, 13. Because we're in the first quadrant, x is positive 12. Cosine B is 12 over 13, x over r. And they already told us that sine B is 5 over 13. Wow, now we have all of the ratios that we need and we can plug them in. Cosine of A is negative 4 over 5, cosine of B is 12 over 13. Sine of A is negative 3 over 5, sine of B is 5 over 13. I know I can reduce the second fraction, but I kind of like that both of these terms are going to have the same denominator with 65, so I'm not going to reduce yet. The first term is negative 48 over 65. The second is negative 15 over 65. Since I have common denominators, I can just subtract and get negative 63 over 65, which is the answer. And I never even knew what A or B was. I just needed to know one ratio and where to go. Simplify cosine of x plus pi. Try this on your own using a sum formula. Look, you already know cosine of pi and sine of pi. Cosine of pi is negative 1 and sine of pi is 0. So this simplifies to be negative cosine x. Let's solve this equation. Sine of a sum plus sine of a difference equals 1. So I'm going to substitute my sum and difference formulas. Hey, look, I have some like terms. Sine x cosine pi thirds and sine x cosine pi thirds added together would be 2 sine x cosine pi thirds. Cosine x sine pi thirds minus cosine x sine pi thirds, that's 0. Okay, now let's substitute what is cosine of pi thirds. That is 1/2. So you're multiplying 1/2 times 2 times sine x. That is sine x equals 1. And now to solve a trigonometric equation, we're going to use the unit circle backwards. What do I mean? In this case, x represents an angle, right? X is between 0 and 2 pi. They used the variable x instead of the variable theta. So we want to know sine of what angle is equal to 1. Well, sine corresponds with the y values on the unit circle. So I'm looking for where is the y value equal to 1? At what angle? Hey, that would be at pi halves. At pi halves, the point is 0, 1. So the y value is 1. Anywhere else between 0 and 2 pi? No. So x is equal to pi halves, and there's only one answer. We can check this by plugging pi halves in for x in the original equation. That also means less writing than plugging it into the second step. Pi halves plus pi thirds is 5 pi over 6. Pi halves minus pi thirds is pi over 6. Sine of 5 pi over 6 is 1/2. Sine of pi over 6 is 1/2. And yes, 1/2 plus 1/2 is 1, which equals 1. So you know that x equals pi halves is the correct answer for this equation.